In this part, we will look at the effect of camber, leading edge radius, and thickness on an airfoil's behavior. This will allow us to guess if an airfoil will be suitable for our design just by looking at its shape. Let's get started. How the airfoil is cambered affects its maximum lift coefficient and the type of stall it has. We have already discussed the two types of stall patterns in the previous video. In general, increasing the camber increases the maximum lift coefficient the airfoil will generate. Of course, this applies to a certain limit. Not just how much camber the airfoil has, but also how this camber is distributed has a huge effect on the airfoil's behavior. For example, increasing the nose camber of an airfoil generally increases its max lift coefficient, and it also increases the stall angle of attack. The lift generated before the stall is not altered much. On the other hand, adding aft camber to the airfoil increases the CL max value and also increases the lift generated at pre-stall angles. However, this also results in a decrease of the stall angle of attack. This effect is similar to deploying of flaps. If camber is added uniformly over the chord of the airfoil, the effect will be a combination of the two effects just discussed. Lift at a constant AOA will increase and stall AOA will also increase. In case of stall behavior, adding more camber usually shifts the stall type from leading edge to trailing edge type. This is particularly true of aft cambered airfoils, as the flow is more likely to separate near the aft portion where it is being turned a lot. The effect of nose camber on stall pattern is not so clear, as the leading edge radius also plays a huge role in determining this. For example, some nose cambered airfoils have a leading edge type of stall, due to the combination of nose camber and small leading edge radius. However, some airfoils like the Clark Y have nose camber but show gentle trailing edge stall pattern. CL max and type of stall are important for takeoff, landing and safety, but we also need to consider the drag in cruise. We want the drag to be as low as possible because an airplane spends most of its time in cruise. We have already seen the CL versus CD plots in a previous part of the series. When the camber is increased, the lift coefficient for which it has minimum drag is increased. The value of minimum drag may also increase. As discussed in a previous video, ideally, when the airplane is cruising, the wing should be flying at the CL at which the airfoil has its minimum drag. Leading edge radius effect. In general, increasing the leading edge radius results in an increase in max CL and makes the stall gentle. Again, this is true only within reasonable limits. For a small leading edge radius, the air has to follow a sharp turn near the leading edge, and this increases the possibility of flow separation. Smaller leading edge radius is used to design airfoils with a lower cruise drag. As we saw in the last video, there is also a compromise here between gentle stall and low cruise drag. Thickness effect. Increasing the thickness decreases the CL max of the airfoil. This is because, in case of a thicker airfoil, the air flowing over the surface must travel farther and turn more as compared to that of a thin airfoil. This leads to the air separating at a lower angle and therefore, the thicker airfoil stalls before the thinner one. The stall is governed by the way the air flows over the upper surface while the lift is controlled by the camber of the airfoil. Thickening the airfoil makes it harder for the air to flow over the upper surface and remain attached, but it does not affect the lift of the airfoil at pre-stall angles of attack. The stall happens earlier and the maximum lift the airfoil can generate is reduced. Within limits, increasing the thickness makes the stall more gentle as the flow is more likely to separate at the aft portion. There is also a trade-off between the drag and weight of the wing while selecting the thickness. Making the wing thicker reduces its structural weight and makes the airplane lighter. Increasing thickness can also increase parasite drag. So we need a wing that is as light as possible without having too much drag. In general, increasing the thickness increases the minimum drag coefficient. But this increase is relatively small as long as the thickness does not become so high that the flow separates. Another benefit of increasing thickness is that the airfoil has lower drag values for a broader range of angles of attack. One would imagine that if the wing can be made strong enough, a very thin airfoil can be used to reduce drag, but this comes with its own problems. A very thin airfoil has a low drag only at a very small angle of attack range. Beyond this range the drag increases rapidly. A thicker airfoil has lower drag at a relatively larger angle of attack range. As can be seen from this plot, the thicker airfoil has a slightly higher CD-min but its polar is flatter and its drag is lower than the thin airfoil over a large portion of the angle of attack range. While selecting an airfoil, we can get an idea of how a particular airfoil might behave by looking at its overall shape. Of course, these are general principles and have exceptions. So it is always better to look at the airfoil plots before making a decision. One benefit of using this information is we can now be better at shortlisting possible airfoils and don't need to look at a lot of plots. One very important parameter not discussed in this part is the moment coefficient, which should be considered to make the design stable and reduce trim drag, but that is a topic for another video. If you found the video informative, please give it a like. You can watch these videos next for more on aircraft design. Thank you for watching.